In this particular video, we're going to see Thevenization process with example 2. So this is the circuit diagram given to us. In that, RL value is 6 ohms, load resistance value is 6 ohms, and if you observe the circuit carefully, it is having different resistors, voltage sources connected in different manner. So let us start applying the Thevenins theorem on this. First step is identify the load resistor, identify the load resistance value and remove it from the circuit. So I have identified the load resistance value. RL is 6 ohms, and I have after removing this RL value from the circuit will look like this. Rest all the things will be there, but A and B will be open circuited. They are not having any connection because I removed RL. Let us go to the next step. Next step is finding the Thevenins equivalent voltage or open circuit voltage. How much is the voltage drop across A and B? So that is VOC, right? So in the previous problem, we noticed that there is only one mesh. But in this particular problem, there are two meshes are available. We can't call this EA, BE as a mesh. This is not a closed path at all. So how many closed paths are there? How many meshes are there? C, D, F, C is the first one. D, E, F, D is the second one. So let us apply mesh analysis method to find the current flowing through this resistor 5 ohm. My interest is to find only the current flowing through this 5 ohm resistor. I am not interested at the value of I1. I am interested at the value of I2 because the voltage drop across this is equals to voltage drop across this plus this. So just like the distance between these 2 points is from here to here, then to here, then to here, because there is no route from A to B directly, just like that, right? So there is a route from A to B, that's A to E, then to this, then to B. As there is no connection between A and B, so we have to find the voltage drop across this. We have to consider the voltage drop across this A and E, and voltage drop across this 5 ohm resistor and 0. That itself is the completely, if you add them, you will get the open circuit voltage. To get the open circuit voltage, I need I2. So we use mesh analysis method to find the current flowing through R4 resistor. First step in the mesh analysis is we apply KVL in the first mesh. CDFC. So minus 2 plus minus 8, 4 into I1, 4I1, 4 into I1 minus I2, minus 8 is equal to 0. That's the first equation. So applying KVL in D, E, F, D, we get D to E. First terminal that I got is plus. So plus 15 plus 3I2 plus 5I2 plus 4I2 minus I1 is equals to 0. This is the second equation. Upon simplifying 1 and 2, we get the value of I2 and I1 as I2 is equal to minus 1.1 amperes. I am not interested to know how much is the value of I1 because that is of no use to me as of now. Voltage across A and B, that is open circuit, is equal to minus 2 plus is minus 5. This is voltage drop across this. Minus 5 plus voltage drop across this is current into resistance. 5 into I2. So that is minus 5 plus 5 into minus 1.1 because I2 is minus 1.1 amperes. So simplifying that, we will get minus 10.5 volts. Alright. So let us move to the second step, that is Thevenin's equivalent resistance. How to get the Thevenin's equivalent resistance? To get the Thevenin's equivalent resistance, we replace the voltage sources. We replace the voltage sources with their internal resistances. If you observe this particular circuit diagram, there are three voltage sources are there. One is V1, the other one is V2, the other one is V3. They are not given with any internal resistance information. So assume that the internal resistance of this is 0, this is also 0, V3 also 0. 0 internal resistance means short circuit. So we replace this with a short circuit, this with a short circuit, this with a short circuit. So by doing so we'll get this circuit diagram. In this, if you observe R1, R2 are in parallel with each other, we can replace this entire thing with one single resistor, that is R1 into R2 by R1 plus R2, that is 2 ohms. Now after replacing this combination with 2 ohms, this 2 ohms is going to be in series with this 3 ohm resistor, right? 2 plus 3, this is 5 ohms. This 5 ohms is going to be in parallel with R4. So then to simplify this, we use R equivalent into R4 by R equivalent plus R4. Like if two resistors are in parallel with each other, we replace that entire combination with one equivalent resistor, that is R1 into R2 by R1 plus R2. Similarly, here 5 and 5 are in parallel with each other. So the equivalent resistance, nothing but the final Thevenin's equivalent resistance across A and B is going to be 5 into 5 by 5 plus 5, that is 2.5 ohms. From the previous step we got open circuit voltage as minus 10.5 volts, and from this present third step we got RTH as 2.5 ohms, right? Let us move to the next step 4. Draw the Thevenin's equivalent of the given network with VTH value and RTH value obtained. So VTH value is going to be minus 10.5 volts and RTH value is going to be 2.5 volts. So this dotted line, this thing, the components available inside this entire thing is the Thevenin's equivalent, that will have one voltage source in series with the equivalent resistance of the network. So the load current IL can be calculated using the formula IL is equal to VTH by RTH plus RL, where VTH value is minus 10.5, RTH is 2.5 ohms, RL is 6 ohms. We get minus 1.235 amperes current. Observe this minus sign, okay? Minus sign indicates the assumed current direction and the actual current direction, both are opposite. I assumed IL direction from A to B, but actually it is from B to A. So if IL is from A to B, the direction of IL is from A to B, that is going to be minus. If the direction considered is from B to A, that is going to be plus 1.235 amperes. This is how we have to understand the minus negative sign. Current quantity remains same, 1.235 amperes will remain same, but negative sign means the assumed current direction and the actual current direction both are opposite to each other. Alright, so with this the Thevenin's theorem example 2 also gets completed. I hope you understood the Thevenization process. So after the completion of this presentation, Thevenization process, student will be able to define what is the Thevenin's theorem. He can able to explain anybody what is the Thevenin's theorem, how to Thevenize the given network, and how to draw the Thevenin's equivalent circuit. Thank you very much.